do something with like just detecting fish that it can fall off, and then control it beyond that, and having one in there and one reason for the rest, and just make it topple over.
Okay. I also did a little bit of research, and I'm also not quite sure what the problem is.
Yeah.
If we need to control the thing on two directions, so either this and this, because this would be very, not very easy, but
Fairly
easy.
easy.
Yeah.
Yeah.
But yeah, I don't know. We should build a row of leg, and we have one over here, one in the knee, one in the hip. But
That's what I assume.
yeah, but that means we can only have this way, right? Forward and backwards, because it's
Yeah, we wouldn't try to do
like
that.
I think we should wait
Yeah, we should wait
till yeah. And then I saw some graphs about acceleration. How can we
Smoothly control
yeah,
the motor.
we get an angle, but we should do it smooth.
Yeah,
And the way
No, yeah, I definitely agree with that.
then we have to see if we because I don't do anything on cameras, because that's the next problem.
Yeah.
Very complex to
I hope we have some way for how this is going to be, but we have to deal with the ping pong ball must be clear from the background, right?
Yeah.
You have to be able to see the ping pong ball, right?
Yeah.
That's it. I don't know. I try to show that maybe.
So, yes, I think we have this little trip today.
Yeah.
Afterwards, we have three, more. Also, in the text I read, they always say you need like it's visual zapping,
It's what?
called visual zapping.
Visual level.
Zapping, like zapping.
Oh, circles?
Zapping.
Okay.
And
Yeah, visual circle. Yeah.
yeah, and they said in the text we need a camera with a lot of frames per second, but we told us we don't have camera. So I think we should wait.
Yeah, we don't have a lot of things to say, but it'll become a little more shy. Alright, well, at least you got some general.
Also, Chinese learning.
All right. So these two guys were first. That's why they are.
No worries.
Thank you.
They're from my wife's friend's grandfather. And this is, what is it, Mid-Autumn Festival. So next week is no class on Monday, the week after that either. So these are the cookies, not cookies. They're pretty heavy cookies.
Yeah.
Have you eaten them before?
No.
No? Yeah. Then they're more like concrete blocks in your stomach. But they taste very nice. And what are they for, David?
So
The mooncakes?
Name?
Yeah.
Chinese name?
No, yeah, Chinese name. And what are they? Why do you hand them out? Why do you give them to people as
Why?
a present?
The reason?
Why?
The Moon Festival.
Okay. And what's the Moon Festival?
Because the Moon Festival. There's a legend.
Mm-hmm. What's the legend?
A story.
Yeah, I know what the legend is. I mean, what happened in the story? So Ron told me it's because somehow there was some war and the valiant general managed to send messages through the enemy lines by hiding them in those mooncakes. And then people will break them open. There'll be the secret message: attack on Tuesday or something like that.
So we should eat them on the day of the moon festival, right?
That I have no idea. I ate them today, but I was hungry. So, and I think they're okay for a couple of days, but I wouldn't keep them in the heat for too long. There's some egg. There's some egg yolk inside.
Thank you.
Yeah.
Are there still the messages?
Yeah, you guys were lucky because you were the last two that I had, and you were the first two foreign students that I didn't have enough for everybody, all the students. But I had class this morning and I handed some out and I had two left. So sorry, David, you missed out. Make one cheat.
Are there still messages in them?
Yeah, from me. Study hard. How come my robot is not climbing yet? Okay, then also you can have a look at those. This is the 3D model that I made. This is what I think I'm going to make because the styrofoam one I can cut within a minute. So it'll be enough. But the general idea is that we now have a oriented edge that the climbing robot can hold on to. So if you're like this, then you would have a good hold. So like this. So if we mount it 45 degrees, if your center of mass is here and you have some force pointing this way, then you'll have very good grip here. But if you're over here, then there's nothing, and you won't be able to grab it here. So that's the idea. So we'll have three markers, one like center, which allows you either way, and one to the right and one to the left. And that's what's in the climbing robot simulator that we developed last week. And this is just a 3D printed version of that. It's actually not patently true. Like for a human, if you hold those up, I could actually hold it like this, right, and push out. That would work, but we'll try and keep it simple for now, just 3 different types, and then we go from there. So then we need to have a wall and mount these on there. Actually, I want to paint those. We need to buy spray paint. Red, green, blue, yellow, cyan. Huh? Can you? Yeah. Can you actually buy spray paint? To paint, you can? It's allowed in Taiwan? Yeah. Yeah, because in Canada it's not allowed anymore. Because so many, if you're below 30 years old, you're not allowed to buy the spray paint, they won't sell you. Because the people tag stuff like, I love Susie, I hate Joe, down with the US. So they don't like the graffiti, but we need to buy some spray paint and paint the styrofoam. It was an interesting thing about rock climbing. The thing that I saw was with one of the professional rock climbers, and he said uh, the a lot of people that are into tech, like programmers, engineers, computer scientists, uh, they like to do rock climbing, and he say that's because, or I'm not sure if he said that's because or that's why, but he basically meant that the the playing field that they have for rock climbing with all the different colors, he said it looks like Mario World. It's like a computer game. That's why a lot of programmers like to go rock climbing there. And once you hear it, you think like, oh, it actually kind of makes sense. If you look at the wall, not the real mountains, of course, but yeah, it kind of looks like Mario World or something like that, right? With all the different colors. And so I thought that was funny. So today I want to talk about the kinematics, and we'll deal with forward kinematics first. And are you recording now, David? Yeah, you're not recording. Okay. And while we're waiting here, these are just some of the routines that are raw, based on last week's homogeneous coordinates and affine transformations class. Rotations around the z-axis, the y-axis, and the x-axis in 3D, so three-dimensional, which means that our transformation matrix is going to be a 4x4 matrix. So this returns the various rotations. Here's translation, and here's the scale operation. I didn't put in a skew, but skew we'll do it. Here is the Danavid-Hartenberg Convention. Transformation matrix, which we'll discuss a little bit of detail. That convention is pretty useful, especially for industrial robots. For humanoid robots, it actually doesn't feel so intuitive, doesn't feel so useful. You can still apply it, of course, but it means that you have to, sometimes you have to do more work than you actually would need, and so I usually don't bother or don't strictly apply it. Then a function that is really useful, allowing you to plot the coordinate system. Anytime you're dealing with 3D problems, visualization is going to be your biggest enemy, because you can sort of think like, oh, this is the world coordinate system, and it's here, and now I shift it to here, but now this is the wrong hand, right? This would have to be a left-handed coordinate system, so you want to change that around. Being able to plot things in Matplotlib or any other 3D drawing program make things a lot easier. And the first thing you want to plot is the coordinate system. It's like the old joke, or the old problem when you start programming in elementary, like primitive OpenGL. Then when you start programming that, then the most common bug is that everything seems to work except your image is black. You don't have the scene, you don't see anything. And the problem then is usually that you paint very nice trees and birds and everything, but your camera is looking this way, and then everything is behind you, so that there's nothing that the OpenGL context will show you. That's a very common problem to have. If you can plot the coordinate systems and print out the coordinates, then you have a lot easier. So here's a humanoid robot that we have in the lab. It's a Thormang it's a Thormang robot from Robotics company, and I didn't bring my robot, but the robot that you build yourself will also look something like that. Right? Maybe not exactly, it'll be simpler, but the idea is the same. So, what do we mean by kinematics, and how does it help us? For the kinematics, that means we're basically talking about the geometry of the robot. As you can see, for most humanoid robots, we have servo motors. The robots that we're building will all have servo motor. That's a motor that's attached somehow, usually via a bunch of intermediate gears, to a sensor that measures the current rotation of the output shaft, and then that allows you to rotate to a particular angle, 0 degrees, 90 degrees, 45 degrees, 50 degrees, so on and so forth. We played around with that last class with the RC servos, which are the oldest technology for servo motors, but relatively, I mean, has some advantages. Extremely common, you can get them anywhere, they're very cheap, and lots of support for controlling them. They're usually controlled using a pulse width modulated signal, and we generated that last time on the Pico. So here with our Thormang robot, as you can see, we have 2 degrees of freedom in the ankles. So we can pitch and roll the ankle. We have 1 degree of freedom here for the knee. We have another degree of freedom. There's this one here, which is the hip pitch, hip roll, and hip yaw. So there's 3 degrees of freedom in the hip. And then we have the arms. There's a torso. There's a degree of freedom here in the torso. Then we have 1 degree of freedom here, 2 degrees of freedom, 3, 4, and then 5 and 6 on the gripper, on the hand of the robot. So for our rock climbing robot, we want to simplify this here, for example, and the rest of the kinematics is probably pretty close to what we want to build. Here's a view of the arm and the upper body of the robot by itself. Now, the problem that you have when you're trying to do a rock climbing robot is that if, can you just help me and hold this? Hold this. Yeah. So if I have some kind of sensor, some kind of camera, I can look at the, or actually you hold this one. Yeah. Then I'm here, I want to reach there to latch on, right? So that I can continue climbing. And then the problem is what we can send to the actuators, what my brain has to solve also the forward and inverse kinematics problem. All I can send are angles, 10 degrees, 12 degrees, 15 degrees. Then the end effector has to reach the point where I want to grip. So, thanks. Somehow we need to be able to map our most important problem is we want to be able to move our hand to the handhold so that we can grip it. Similarly for the foot, right? And similarly for the head. Except with the head, you usually don't want to grip things in climbing unless you have very strong neck muscles. But you want to be able to look at things, right? I want to see what's up there. So I need to rotate the camera. That particular problem that I just described is actually the inverse kinematics problem. So this is a problem that we'll be looking at next class, but we'll start first with the forward kinematics problem, which is the version where if I send 90 degrees to my shoulder and 0 degrees to the shoulder on this joint, and 45 degrees to my elbow, and whatever, 45 degrees on the hand, then where would my finger point? What would be the position relative to the robot? Or if we have the robot localized in the world coordinate system, then of course that would also allow me to say where that is in the world coordinate system. So in order to be able to answer that question then, first we need to have a couple of definitions, or we need to think about a couple of things. First thing is, if I want to move my, if I want to figure out what the position is of my hand, right, of my finger, given the different angles that I send to the arm, or that I send to the robot, then what about that position? The first thing would be that actually any motor's command that I send to my left arm has no impact on where my right hand is going to be, right? Like these two are completely independent. So we can come up, or we have the concept of a kinematic chain, which means from the inertial frame, which is the world coordinate system, to the robot. Then from there, we follow along a set of joints, and then at the end of it, we have the end effector, and that's the position that we're interested in. That's what we're trying to calculate. There's several kinematic chains on the humanoid robot. So for example, here we have the left arm, we have the right arm and the left arm, and the two of them are completely independent. What about the legs as far as the position of the arm is concerned? Yeah?
The legs could influence the position.
Yeah, exactly. So the legs and the torso are actually coupled as far as the kinematic chains are concerned. That makes things a lot more difficult. So if my finger is here and I'm balancing on one foot, then I can move this leg all I want and it will be okay. Right? It won't have any impact. But if we have a closed loop, which means through the ground, now the two legs are, depending on where my center of mass is, if I move my knees, the position of my finger is also going to change. Right? Figuring out the exact effects is non-trivial because it requires also knowledge about the dynamics. Usually, you need to see, like, is this foot actually in the air because I'm leaning over too far, or is there some weight on it? And if I move that knee, then the whole center of mass is going to change. So to simplify that a little bit, we will, what do you suggest? What can we do for this particular robot? Or when you build your own humanoid robot, then how would you deal with your own robot? Well, we can try and minimize the impact of the kinematic chains. So, for example, if we put the center of mass, the origin of the robot, the origin of the coordinate system here into the groin of the robot, which is a popular choice, then I have one kinematic chain here, one kinematic chain there, and then I would simply calculate the position of the legs and then figure out which one of those is on the ground afterwards. Right? That is not exactly correct, but it's a good enough approximation to work. And then here we have another problem because here there is a degree of freedom in the torso. So the robot can rotate this way. And now that means that the right and the left hand are sort of coupled with this torso joint. For the forward kinematics, where we're given a set of joint coordinates and we're trying to figure out the position, that is not a big issue. It's more of a problem for the inverse kinematics because if I just want to move this finger to this handhold, ask you again to hold these up. If I want to move this finger to this handhold, then I could rotate like this and I would hit it, right? But I also want this one to stay there. So then if I calculate this one, and I rotate it this way. Now this one is gone again because of the couple joint here. So then you need to come up with a way to avoid that. And we'll look into methods for doing that when we discuss the inverse kinematics. For industrial robots, for example, they have it a little bit easier because you can design the industrial robot not based on a human blueprint. So we usually build the industrial robots in such a way that the kinematics are as easy as possible. So all the joints are exactly 90 degrees, and there's no closed loop kinematics. That makes things a lot easier. Of course, and many automation systems work that way, but if you want to do interesting manipulation, dexterity, so you want to do things like this, so you can flip them over, then you really need to have two arms, which means that you usually end up with closed loop kinematics. But there's lots of research still ongoing or sort of blew up now because of the importance of dexterous manipulation. Non-intuitive manipulation, which I think is crucially important to robots in the future. All of those motion plans for doing this kind of dexterous manipulation, they require a closed loop kinematic chain, and this is a very hot research topic at the moment. We are very sort of really just at the beginning of trying to understand how humans can do that and things like that. I always have an example with my office door upstairs. Before I had an office upstairs in the fourth floor, and there if I ask students, okay, we have a humanoid robot, I want it to be able to open a door, then I could tell David or anybody, and then 2 weeks they will program, the robot will walk to the door, will align with the knob and will turn it, and then go back and open the door, and that will work. With the door at my office, I had the turning knob, so I had to turn the knob, which has a spring, and then there was a spring latch. So I had to pull in the key and turn the key so that the latch will go back, then I can open the door. Okay. So there again, that would be a closed kinematic problem, first of all, but for humans, that can be solved easily. We do it subconsciously, it's not a big deal. But with this particular door, that was fine until I actually carried a laptop, because then you're carrying a laptop and there was no table there or anything to hold down, right? So to open the door, now how can I turn the knob and turn the key at the same time while carrying the laptop? So what I did is, in order to get into my office then, I carried the laptop, and I figured out that with this particular door, first I can turn the knob, then use my knee to brace it. So I use my knee to hold then I can take the key, open the latch, and then I can open the door. And the interesting thing about that is that I could have asked 100 students. None of the students, if I tell them, oh, I need to open the door with the robot, none of them would have come up with this motion. No way. Right? It's not something that you think about having to use the knee to turn or lock the turn. No. But humans are very good at this, right? So we can come up with very what I would call unconventional manipulation or dexterous manipulation to make things happen. If you have to pick up small things like stamps or little pieces of paper, right, then we're also quite good at it. But it takes a while until you know exactly how you want to do it. Or you can just wet your finger and put it on top and then pull it up that way. So this manipulation for humans is one of the really interesting. This kind of dexterous manipulation, I feel, is one of the most interesting problems for robotics in general and humanoid robots in particular. And it's also important because it is usually it's a multi-step process. So you need to actually plan through a set of actions before you can reach your goal. In order to open the door, it's not like I can just do this one motion and then I have to first lock the door, then I need to do this, then I need to do that. So the kind of AI systems, the large language models, the neural net, deep learning architectures are really not that good at doing reasoning about future states from actions. And I think that there's a lot of possibility and potential there for interesting research. So if we want to control it, we need to know the effects of our control. For humanoids, we use mostly servo motors, so we have 1 degree of freedom. Technically, we call them revolute joints, and the angle between the two links can be controlled. There's also a possibility of more complex joints. For example, like a human shoulder, to combine multiple axes of rotation is a possibility, like here 3 for the shoulder. And there's also some robots use linear actuators where the actuation is not actually a rotation, but is actually an extension or a contraction, like a translation in your between the links. And when you think about it, what kind of actuations do humans have? Revolute joints or linear actuators? Yeah?
Revolute joints.
Yeah, you would think so. Why?
Because we can extend our hand.
You can extend your hand whether you have a linear actuator or a revolute actuator. Yeah, so you rotate like this. So you think this is a rotation, right? For your elbow, this would be a rotation. Yes, you can certainly model it as a rotation. But how is that rotation actually achieved? What rotates your elbow?
The muscles.
The muscles. And how do the muscles work?
Extract and extend.
Yeah, so muscles can only extend and contract, which is a linear motion, right? So the human body, we actually have linear actuators, our muscles, that are connected to the bones via tendons. And those are the ones that result in revolute action then, revolute joint. So it's quite interesting. So, for humanoid robots, actually, for a long time, people have thought that if we use linear actuators, we will get simpler motion or motion that would look more closely to what more like a human motion. And there were always lots of claims about this. But linear actuators were much more expensive, much more complex. So they weren't used that much in robot design. And if you look at the Unitree G1 and the motions that they have, they're clearly still robotic motions, but they're extremely close, much closer than anything we've ever seen with linear actuators. So now sort of everybody has focused on the fact that for the human kinematics, at least, we're dealing with rotation. For 3D printers, of course, you're dealing with linear actuators. CNC machines use linear actuators. So here's one project that we did before. We taught the robot, our Thormeng, using a network. We actually taught it how to type on an arbitrary keyboard. So the robot can find the keyboard on the table, any kind of keyboard, then move it into the right place, and then it'll start typing. And there on the left-hand side, you can see the reinforcement learner running through simulated movements of the robot. So then they can use the keyboard. It's trying to identify the keys and work out where they are. The crazy thing about that video is that it's by far my most popular video. And I have much cooler videos, I think. Let's see. 5,300 views. Somebody is even making money off this by playing advertising. But 5.3 thousand views blows my mind, really. I guess I could be called an influencer, and then because I have 30 students in the class and I have 15 views on my lecture notes or lecture videos, and here, do we have comments? Yeah, so lots of people are asking me to commercialize it from India, and I think they want to pay €1,000, and I think it's all like spam farms or something. People that are running 100 phones accounts at the same time. Yeah, this is more my line, 90 views. The archery Much cooler project, 500 views. Oh, somebody else did a typing robot. And it's a more popular problem or topic than I imagined. So forward kinematics, given a set of joint coordinates, figure out what the position of the end effector is, where the end effector will be the last link in your kinematic chain. Inverse kinematics, set the joint variables so that the end effector will be at the correct position. We simplify things and we assume that each joint has 1 degree of freedom. If we have a joint module, one, for example, that combines multiple degrees of freedom, then we simply model that as 1 degree of freedom, followed by another 1 degree of freedom with a link of length 0 between them, if we wanted to. So we still order all the joints along the kinematic chain. That means that each joint that we have in our robot, we can use one number to describe the state of the joint. If it's a revolute joint, then it would be the angle of rotation for our servo motors. If it's a prismatic joint, it will be the distance of the extension or contraction of the prismatic joint. And we're trying to calculate what the cumulative effect of this set of joints is. So for humanoid robots, we usually have 5 kinematic chains. Left arm, right arm, left leg, right leg, and the head. There may be a couple of joints in the torso that then would be coupled for head, left right arm, and right arm. Now, because this can get very complicated very quickly, it helps to have a schema or a convention for how to label things. That makes it a lot easier to talk about them. So if we have a kinematic chain with n joints, then we apply or we set them or we model them as a chain which has n plus 1 links and n joints. So if I have something with 3 degrees of freedom, then I sort of model it. Then here would be a motor. Then here would be another motor rotating in the other rotation. And here would be 2 big. Then this would be link 0, joint 1, link 1, joint 2, link 2, joint 3, and link 3. We don't have to call them that, but it makes things a lot easier. And now we have it set up in such a way that if I change joint 1 or joint I, then the only thing that will be affected will be the position of the link from k minus 1. So joint I will connect, joint 1 will connect link 0 to link 1. Joint I will connect joint K will connect link P minus 1 to link K. Most importantly, if joint K will not affect the position of any link from 0 to K minus 1. So joint 3 will only affect the position of link 3, joint 4, link 4, joint 5, link 5, so on and so forth. Anything going up, anything below that particular joint will not be affected. That's a key feature. That's why we label them along the kinematic chain like that. So that helps you figuring out what the effect of the different joints are. Each joint does impact the position of the links K to N. Each joint has the joint variable that defines the state. And then we need to attach coordinate frames to each one of the links, because that will be the position of the link that we're interested in. And that means that these coordinate frames are the coordinates of link I, they are constant within the coordinate frame of OI, the coordinate frame that's attached to the link. Because if the link moves, the coordinate frame will also move. So it will always remain the same. The frame that is attached to link 0 is called the inertial frame or world coordinate frame. So that's where everything happens. The inertial frame is the one that is basically your workspace. If you have a mobile robot, then it is it's done a little bit differently. For humanoid robot, for example, our inertial frame would be the one that we attach to the groin of the robot. Right? So that would be my frame here. Then I can still model the robot as a movable base, so I can move within the actual workspace. If our workspace is this room here. Now I'm at location 2 meters, 15 meters, 1.2 meters above the ground. Right? Now my position has changed to here, but my state is the same. I don't want to have to recalculate all of that. So there's sort of two levels if you have a mobile robot. If you have a humanoid robot that is stationary, then you would just have the inertial frame mapping to the world coordinate. So then this would be your workspace, and you need to pick up water bottles from here and put them there. Right? Then these would be the coordinates of the water bottle, where it is, where you want it to be, and you need to figure out the kinematics with respect to that. But for a mobile robot, there's one extra level of indirection. There's sort of the entire workspace that the robot can drive through. So here's an example of the kinematics formulation with 5 joints, and those are all in the same plane at this point. So we just label them. So origin, so it's 2-dimensional. So I plotted in the coordinates of the coordinate system, x and y, and then this would be the coordinate system 0, 0, the inertial frame. Link 0 gets us to the first joint. This would be joint 1, then link 1 to joint 2, link 2 to joint 3, and we have coordinate systems attached there everywhere. And as you can see, what we have with the robot because the only actuators that we have are prismatic joints, which would result in a translation, and revolute joints, which result in a rotation, we can model all the changes in the kinematics. We can model those as homogeneous transformations. So that means any kind of kinematic I can describe using a set of homogeneous transformation matrices, which means that everything can be described as a 4x4 matrix. So then the coordinate frames can individually be connected by the homogeneous coordinates. So from coordinate frame I-1 to OI, I can be connected with the homogeneous transformation matrix AI, and that describes the position of OI with respect to OI minus 1. But it is a function. It depends on the joint variable. It depends on exactly one joint variable, Qi. Then, like we said last time, we can combine our transformation matrices. So the cumulative transformation, the transformation through all the joints from I to j, is written as Tij, and that would be the transformation from I to I plus 1 plus 2 up to Aj. And that's a convention if I is less than j. If it's the same, then it's the identity matrix. To go from joint 2 to joint 2 makes sense to say that we don't need to do any transformation. So in that case, we just have the identity matrix. And if I is greater than j, that means we're going from joint 5 back to joint 3. Then that means we're looking at the inverse of that transformation. And again, all of these a's here actually have an implicit argument on qi plus 1, qi plus 2, uj1, j minus 1, 2j. So they're all functions. Now, one thing that you may realize is that actually this should be wrong here, the way that I model this. Because when we talked about so here I would have transformation matrix AI. Here I have A1, A2, A3, and then here that would be the end effector position. The point of the finger or something, whatever I pick as the coordinate of my end effector on the gripper of the robot. And if you want to multiply, or if you want to calculate it, then we said we can combine the homogeneous transformation matrices. So first I will do A1, right? And then I was very explicit, if we then do a translation on this coordinate frame, which is the one that we get by going from A0 to A1, right? If we then do any transformation on there, then we have to left multiply, right? So if I do a translation here or a rotation, then it should go, it must be left multiply. Now actually here, I write it down right multiply. So which one is correct? if I want to model this, right, then let's say here's the origin of my coordinate system. So this would be the inertial frame. That would be link 0. Now, it does make sense to align in theory, I can put the coordinate frame responsible for joint 1. I can put that anywhere I want. I could put it here, and I can say this is the origin of frame 1. And then, if joint 1 rotates, then this thing would rotate as well. So that's certainly possible, but it makes visualizing things very difficult, and there doesn't seem to be any advantage to it. So the first convention that we follow, which is also part of the Denevit-Hartenberg convention, which we'll discuss a little bit later on, or if you have done Denevit-Hartenberg before, then the first part of the convention is that we align the coordinate system with what's called the axis of actuation. So I put, when I have a revolute joint, right, then I put the coordinate system at the point that I'm actually rotating. Otherwise, the whole coordinate frame will rotate with me, but here it'll be just easier. I can just read off what the coordinates are. I don't need to do any translation. And the z-axis is our axis of actuation. Now in 2D I don't have a choice, right? But in 3D I can rotate. I know now where the position is of this coordinate system, but I could align it any way I want. I could rotate it. So instead of doing that, we always align it in such a way that the z-axis, our rotation, we're rotating around an axis, we make sure that we're rotating around the z-axis. Always. That just makes it much easier then to see what's going on with your matrices. And you can also solve it if you really don't like z. You could, in theory, use the x-axis in all your joints. Some joints rotate around x, some joints rotate around y. It'll get very confusing very quickly. So we always have the rotation axis for revolute joints be the x-axis. For prismatic joints, where we translate, where we extend and contract, we make the extension and the contraction around the z-axis. And that's just the convention to make our life easier. So in 2D, since I've drawn it here on the onto the whiteboard, we'll do it in 2D. How do I get from my inertial frame to O1? So O0 to O1. Yeah.
You multiply the A1 to the origin.
Yeah, but what does A1 look like?
translation.
First, a translation, right? Because, and that's where I sort of deviate from the Dennevit-Hartenberg convention. Dennevit-Hartenberg, the way that you translate is along the x-axis always. But actually, that nowadays doesn't really make things easier, I don't think. So I can say, okay, I'll translate here by Tx and here by Ty. Right? I can model this as two separate translations. And I don't really care whether this, otherwise I would have to rotate this to make sure that the x-axis is aligned there, so that I can just move along x to get to the next joint. That's the main part of the Dennevit-Hartenberg convention. For this robot, we could easily do it, but there's, as we'll see in a couple of minutes, it's not that easy for humanoid robots. It leads to some problems. So here, what I need to do is I need to translate by Tx, Ty, and then
rotate the origin.
and then I need to rotate, right? Because if I just translate this here, this won't align with the zero axis there. Or here, this would actually be fixed. This one here will be, this angle will depend on what my joint variable theta 1 would be, right? So we want to do a translation and then a rotation by theta 1. Now, these are homogeneous coordinates, so I want to left multiply them, right? But actually, no, that's not correct, right? Because what is this? R theta 1. That's how it is. Our rotation is a rotation around, no. Yes, it's around the z-axis. That's correct. It's a rotation around which point, though? The point that corresponds to the z-axis, and that means it's the origin, right? So rotation is only rotation around the origin, right? So how do we rotate around an arbitrary point? Because the point that I want to rotate around is not the origin, it's this point here.
So we rotate first and then translate. So we rotate.
But then my translation will be off. Because if I rotate first, this wouldn't be Tx, Ty anymore. If I want to rotate around an arbitrary point, P, and I have some points here, a little house, then how do I rotate around point P? By 45 degrees, so I should end up with this. 45 degrees of here. We did talk about how to do the rotation around an arbitrary point, yeah?
We moved the origin to P.
We move P to the origin,
Yeah.
yes. Same thing. So if I want to rotate around point P here, what I have to do is move first P to the origin, which is the inverse of moving the origin to P. If TP is the origin, is the translation from origin to P, then TP minus 1 would be the inverse of that. Right? Then we do our rotation, and then we need to translate it back. Right? So now I have this, then what do I need to do? Yeah, so now I want to do the rotation here, right? This rotation, but actually it has to be around this point here, Px, Py, right? So what I end up with is I get T, Tx, Ty, and then what I want to apply is this rotation, but this rotation looks like this. It's around the point Pxy. So first we translate xy to the origin, then we do our rotation, and then we translate it back. Right? Now this is the identity matrix. This one cancels out. I bring it to x first, and I bring it back. Do the rotation, then I bring it. So that means now when I look at it, it looks like we're right multiplying. We're right multiplying the matrices. Right? But really the only reason why we're still, the homogeneous transformation matrices are correct. You need to left multiply them. But because we're always multiplying to the point that, rotating around the point that we translated it to when we're doing this kinematics, that means we can simply right multiply them. Like this will work for anyone, right? Everyone in the chain is going to go through this. So that's why our transformation matrices here, rotations, translations, are going to change. Or you can combine them into a single one variable with a single 4x4 matrix with the one joint state variable. This is all we end up having to do then. So you can actually go along the kinematic chain and right multiply and apply your translations and your rotations, and you're going to end up with the correct target location. So here we need to go from O0 to O1. First I need to translate to there, and then I need to rotate. But we need to rotate around this position here, Tx, Py, not around the origin. So we end up with the translation. Then we rotate around that point, and then we calculate the compound transformation. We left multiply them, but the rotation around the point, so the point rotation, that consists of the inverse translation, the rotation, and then the translation, which is why it looks like they're flipping sides. And of course, mathematically they do, but it's not like we're all of a sudden deciding to right multiply things. It is correct. So the end effector position then will be O from 0 to n will be the position of the end effector in the inertial frame. which is a 3 by 1 vector, and then we have a rotation matrix, 3 by 3 matrix, that takes us from the inertial frame to the position of the end effector and changes the alignment of it, like the angles. So this H is the cumulative effect of all of these transformation matrices multiplied together. They are either rotation or translation matrices, which means they either affect this point here, this 3 by 1 vector, which corresponds to the position, or this 3 by 3 rotation matrix. Now that rotation matrix defines the relative orientation from link I to J, and it consists of all the rotational components, and the coordinate vector corresponds to all the translational components. So we have a 4 by 4 matrix, but we can break it down into sub parts of that matrix that define or tells us, well, if you want to know the distance, for example, from the origin to the end effector, then you can just look at the last 3 by 1 column. So here is a small sample problem you can work on for the leg of a robot, where we have the torso, link 0, joint 1, 2, and 3, and then here's O3, and you're trying to figure out where's O3 with respect to the body of the robot. So then here I can change the angles and it will tell you what the position of. This is the inertial frame in 2D, joint 1, joint 2, joint 3, and the end effector, joint 4. And oh, that's a picture that I already drew. So that's it as far as the forward kinematics are concerned. So this allows us to calculate the forward kinematics easily. Now, one thing that is interesting, especially given this course where we're using simple manufacturing methods, either 3D printed or just cutting things by hand. One of the things is that in order to calculate the kinematics here, I need to know the joint coordinates, which I can actually change, of course. Right? But the other thing is I also need to know the link length in order to get the translation matrices correct. Now, if you have a CAD drawing of your robot, then that's not a big problem. But let's say somebody gives you an OP3 and Robotics has gone out of business and you can't get the CAD drawing anymore, then what would you do? Or, also, let me just talk about Henry Hartenberg. Here's one example of where the Denavid-Hartenberg convention, which is right now the only convention that I imposed was that the axis of orientation, well, first of all, the numbering, right? But that's a minor point. That makes sense. Like joint 1 goes to joint 2 goes to joint 3 is much easier to remember than joint 1 goes to joint 7 goes to joint 2 goes to joint 5, even though you could name them that if you really wanted to. But in reality, we want to assign them that way. The other convention that we have that make things a lot easier is to actually put the coordinate system so that the axis of orientation is defined. Rotation is a rotation around the z-axis, always. Don't need to worry about where your joints are oriented or anything like that. If it's a linear actuator, then your axis of it extends and contracts in the z-axis. That's also very reasonable. Now, for the Denavid-Hartenberg convention, they go a bit further. They go a lot further, actually. And the motivation for it also kind of makes sense, because that transformation matrices, those are all going to be 4x4 matrices. So in theory, we have 16 unknowns, 16 numbers that I need to know. Well, not really 16 numbers, because the last row we know. Right? We're not doing anything with perspective distortion, so we're just going to use 1 as our constant factor there. So that's okay. We have that. But we're still left with 3x4, 12 unknowns. 3 for the position and a 3x3 rotation matrix. Now, that's a lot of numbers to try and figure out what they should be. So Denavid-Hartenberg manages to do that by only providing 4 numbers. And then for industrial robots, you can often find these four numbers in the documentation. So they tell you exactly what the Denevit-Hartenberg parameters are of each joint in your industrial robot arm. And you can calculate those matrices then a little bit faster, the idea was, because you can calculate every transformation matrix just using those four numbers, and it gives you exactly the structure for it. Nowadays, I can do all the computation first and then test them, so there's really no speed benefit anymore. But a couple of things that are annoying. Now, how do they get it down to just four numbers? I thought one of you guys already did the Denevit-Hartenberg kinematics thing. So how do they get it down to four numbers?
One number is the joint angle, but it's variable.
So one number is there's two numbers that may correspond to the joint state. One is, if it's a revolute joint, then it will be the theta angle, yeah. In our case, there will be a number theta I, which corresponds to the rotation angle. So that's always a variable. Yeah, then?
Yeah, I think normally you project it on a XY coordinates, so we have the translation in the X and in the Y.
Yeah, so, not quite. You assume that for every system that you have, the Z I minus 1 axis is going to intersect the XI axis at a 90-degree angle. You always make that happen. So that means that to get from joint I minus 1 if these are both revolute joints, to joint I, you, of course, you can just do this translation, right? Whatever that is in 3D. This is not 2D, this is a 3D graphic. So it's a little bit hard to see. But according to Denevit-Hartenberg, you always go along Z first, and then, since they intersect, you go along here, then you go along this X direction here to go to the new joint. And then lastly, there's a rotation here around the X alpha. So this is done with angle alpha. So there's two distances and two angles that you always use. But you have to go along the z-axis, and then along the z-axis you hit the next x-axis, and then you go through there to the next joint. If you have, so these are the four numbers that you're dealing with. One would be the rotation here, theta I minus 1. Then you have a displacement that's usually called d along the z-axis to go to the point where you can switch over to the next coordinate system. Then you go along the x-axis, and then there's a linked twist in order to align them. So that's how you end up with four numbers. If you have a prismatic joint, then your joint variable is not this rotation, but it will be this displacement here. Because here, if Z is our axis of actuation, and I push or contract along the z-axis, then that will change this displacement here, this d. So if we look at the joint here, this joint, for example, here the z-axis will be going out this way because the shoulder rotates, right? And then the z-axis here has to go down from this z-axis because they have to intersect at a 90-degree angle. So that then defines the orientation of this joint. So here everything is okay between those two. No big surprises. What about this one here? From here to there? Right? Actually, in a sense, it should be easier because the two z-axes are parallel to each other. Right? They're both going in the same direction. This is like this shoulder joint. This is this elbow joint. So they both rotate in the same plane. So this joint here is going to, z-axis is going to go either out or into the paper, depending on how you want to model it. This one is the same. Now that means that there's an infinite number of x-axes I can draw between those two. As long as it hits the other x-axis. But I'm not allowed to go here and then down. I have to point this x-axis to go directly to this joint. Because I can only do one displacement. Here, there's only one number that I can do along the x-axis. And along the z-axis. Since they're parallel, there will be no translation along the x-axis. The coordinates are not going to be shifted this way or that way. It doesn't make sense. We just stay in the middle of the joint. So you need to then align everything. You need to calculate this angle here and this distance, and then figure out what that is in a straight line distance. And that just makes it harder than just looking at the schematic. Okay, here the dimensions aren't painted in, but if you look at it in a CAD drawing, it'll actually tell you the distance from here to there, and it'll tell you how far down this is. So I think nowadays with the compute hardware that we have available, you can just pre-multiply these matrices and be done with it, and the impact on your performance is going to be negligible. I don't know what kind of processor you would have that wouldn't be able to do these matrix multiplications much faster than it can access memory. And then you don't need to, then you sort of follow, it follows more intuitively what this point here does. The thing becomes then more tricky, or with humanoid robots. Now, let's say you modeled this arm, or you modeled the right arm. Right? Now you want to model the left arm. Yes. So now then how do you model it? You need to have one joint here, right? Because definitely I can rotate my shoulder this way. And then you need to have one joint here, right? But when you actually try and debug your robot program, then quite often, robotics is a tough domain to develop software in. One reason for it is because if you write some kind of business logic, right, or anything like that, then you make some access to the database, that key doesn't exist, then the whole program will crash. So you get a core down, right? Or you're trying to sort some elements in an array, but in order to print out the list of top performing employees that get a gold star, something like that, if you get this wrong and your array indices are out of bounds, Then if you use a programming language like C or C++, actually C++ has checked access into arrays. If you do that in Java, it's not a problem, right? Boom, it's going to give you an access violation, right? And everything is great. Like, I mean, not great, you have a bug, but the program will stop, it'll say access violation, array -7 doesn't exist. Then you can find the problem. With robotics, it's very different because for a lot of the things that you calculate, the kinematics, for example, the inverse kinematics, the dynamics, the computer vision part, what you usually have and what your output is same thing for deep learning. We do a whole bunch of matrix multiplication, right? And then we print out the numbers. So usually when you debug, if you get these matrices wrong, right, then your program is not going to crash or anything like that. Your program is simply going to keep running, but it'll give you numbers that don't make any sense. And you think your robot finger is here and just touching the button to cancel self-destruct, whereas the button is over there, boom, the whole world goes up. And it's all your fault. So it's very difficult because mostly you have thousands of floating point numbers that fly by and you're trying to figure out what the heck just went wrong, except you know your finger is not in the right position. So making that easier so that you understand what these numbers mean actually helps a lot in debugging. It's like one of the best things you can do. After, the best thing you can do is actually visualize what these numbers are by drawing the coordinate systems. But if you can't do that, if you only have a shell, for example, you don't have a window, like you cannot draw graphics, not so easy. But at least saying, okay, if I rotate this joint, it's right now at 10, it's a little bit too low. Maybe if I bring it to 12, then that'll work. Then it's already very useful if you can figure out where a plus leads you. Like, if I increase the angle, is it going to rotate up or down? Right? So if you align the coordinate systems in such a way that this one is pointing forward, this one is pointing forward, the way that the robot is built on this axis, that would work, right? Because you have the servo motor and no, it wouldn't work. You have this servo motor, it's going to rotate. So if you increase, if your rotation is counterclockwise, which is what most of them are, then I would be looking at it this way. So positive would rotate it this way. Right? But here, then I'm looking, it would rotate it this way. So here the arm goes down, here the arm goes up, if I change it. So then you need to know which direction the bloody arms are, which arm you're currently talking about. So that makes this symmetry for humanoid robot makes it annoying to try and figure out what the joint coordinates are. It's very difficult to say, we have some problems in our kinematics. Let me just see what I need to turn a valve or something. I just want to find the position of the valve so that one of the FIRA competitions, you have to turn a lever. Okay, so the robot, it's theoretically easy. You just walk there, you look for the valve, and then move the hand and bring it down. Right? No complex motion planning, nothing like that. But during the competition, when you're trying to debug this at 2 o'clock, it's a lot easier if you can say, okay, I'll move it there, and then that should bring it in the right position. I'll just add it to my code. Hopefully it'll work tomorrow when we have to run the competition. That's also difficult to do with the dynamic Hartenberg because all the axes are much more defined. Um, you can have, so usually we have the right leg and the left leg, and we just mirror the X and Y location. That means we're actually, for the left leg, we have a left-handed coordinate system, but at least our angle rotations work the same way. That up, leg out is the same for both the right and the left leg. Increasing it will bring it out for both of them. That's much preferred to here. If I increase the angle, the leg is going to go out. Here, if I increase the angle, the leg is going to go in. Right? But there's no way. So basically, because of this symmetry, we have a we're rather flexible. Like, I'd rather have that being intuitive and then having a non-standard coordinate frame or non-standard alignment of the coordinate frames. So then we can rotate them. So then one Z coordinate is pointing this way, because the only other way to do it would be a left-handed coordinate system, which we've done, but that's also not so good. But then one of them points out this way, the other one points out the other way. Then at least plus and minus has some meaning in your control. So that's just from a practical point of view. The things that make it not so nice to deal with with the humanoid robots kinematic chain. But this would be the chain that we calculate here. From our inertial frame, first translating, this is our origin of the torso, and then 0.3 meters from here to there. Then if X and Y is aligned correctly, then I have to go 0.3 meters down along the Y-axis. Then the first rotation angle, -40 degrees. So here's the -40 degrees. Also remember that where you have to deal with radians always when you store angles in the computer, they should always be in radians. Only when you print them out, you convert them into degrees. Makes your life also a lot easier if you have a convention that you follow. Then from here, we're going to 0.7 further along here, along the x-axis. So this is what I aligned. So 0 degrees would be here, just like the x-axis, and now I rotate it -40. So from here to there, I'd follow the x-axis with 0.25. Then we rotate again, and we can follow 0.2. And then here the ankle is a little bit different, right? Because the origin point, the end effector point on the foot, would actually be here, the center of the foot. So I just need to go down by this distance. I don't really, I can calculate the whole area of the foot if I have to do collision detection, for example, or if I have to calculate collisions, or if I have to calculate sometimes, or quite often, very often, we want the robot to walk. Makes sense that the foot is parallel to the ground, right? So that we have good, good traction, good landing. If you land like this, you're just going to fall backwards. So if I want to make sure that the angle is parallel to the ground, then I can do that. I can calculate what the angle is. I can estimate. I can, in the simplest case, I assume it's 90 degrees to me, and my torso is exactly in the center. If I have a 3D camera, I can measure. I can get exactly the terrain slopes. Now, one thing that we would like to do would be, I will take that and set that up a little bit differently.
Can I ask one question?
Yeah.
What does the point dot operation do? Is it like right multiply?
Yes, that's a dot product, is uh, which is just the matrix multiplication. The dot product between two matrices is the matrix multiplication. The reason why I use dot here is you have NumPy has NumPy arrays. We have NumPy arrays. But those are just arrays, so I can have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Right? If I have a NumPy array, A and B, then what do I get if I multiply A times B? Yeah.
The product of like if A column 1 row 1 times B column 1 times row 1 column 1.
Yeah. I get the piecewise multiplication if I write this in NumPy. Right? This is legal. There won't be, that's why I say it's a problem debugging things in robotics, because this is a legal operation. NumPy will execute this at lightning speed even, but it's not what you expect. The output would be 0. 0 times 9 is 0. 1 times 10. 2 times, why did I draw 21? 11. 22. 3 times 12, 36, so on and so forth. Right? That's an operation. It works on matrices, but it's not what you expect. Right? So, NumPy also has a matrix class. So, the matrix class would do that. So, instead of np.array, if I go np.matrix, then I can do A multiplied by B, and it will be the correct matrix multiplication. But there's a couple of, in my view, disadvantages of doing it that way. One, it gets confusing what kind of multiply you're now doing. It looks nice and concise, but unless you're sure, like I write some code for doing forward kinematics, and then David is using my program. He says, oh, I just pass in A, and he passes in a NumPy array instead of a matrix. Then we get the wrong behavior, right? So then I have to check whether this is really a matrix or just a two-dimensional thing. Sometimes you read in a list that you don't even want to convert to a matrix. NumPy will still deal with that as if it were an array very easily. You don't need to do anything special. So if David sends a list of lists, it will silently cast it to a NumPy array to make it match this operation, so there won't be any error. But it will completely fail if you're trying to do this on a matrix. It doesn't do automatic casting to a matrix, I don't think. Actually, I haven't tried that, but I would be surprised. And the other problem is that the matrix class has much fewer methods available to it than the array class. Array class, we can extend, we can resize, we can reshuffle, we can stack one on top of another, all kinds of powerful things that we can do that the matrix class doesn't have implemented. Because usually it doesn't make sense for a matrix to do these things. So, I mean, up to you, but given those disadvantages, I like to keep the whole code to be NumPy arrays, nothing else that always works. Then I know what kind of data I'm getting. If I get a matrix, NumPy will cast it to a NumPy array if it expects that. And the only problem then is how to do this, how to do the matrix multiplication. And so the only disadvantage is that instead of writing this, I just have to explicitly say, which I actually like better, right? I have to explicitly say, I want you to use matrix multiplication for this multiplication. If I write this, then I actually mean the piecewise multiplication for elements. And then I don't need to read code and figure out what kind of multiply I now want or is executed. And I think lots of people in robotics are doing it this way. But you may read code where it's like this or with an at symbol, which is also another shortcut for doing the matrix multiplication. I just got used to just using dot product in order to do the matrix multiplication, the way that you expect it to be. And of course, also the nice thing is that it gives you right and left very clearly too. And you can chain them, so you can go like, I don't really need to do this, I could just write acom dot a1 dot a2 dot a3 dot a4 dot a5, so I can combine them together. And this is not just as a lesson for NumPy. Other frameworks, other programming languages have other conventions. So if you program in R or Julia instead of Python and NumPy, you also have to be aware of what kind of multiplication you do. I think Julia actually, which would be quite an interesting programming language if you want to learn a new one. I think they have proper semantics for all the matrices, and they actually, yeah, so they just have multiply overlay. one, two. Oh, they don't even have a comma between the elements. It's like separated by space. That can't be right. Ah, yeah, 1922. So let's just see here what we can do. So let's say you get a robot, or you don't have access to the cat. Then what can we do? Okay, so yeah, let's change this. And the thetas I have a -40. -30. Just copy this one. And then my cumulative matrix, first I need to rotate. First I did the translation. So This is one, should be like this. Feed out. And the first one would be to move it from the body. So this one is actually translated into 0. Now if I want to have the position, then I just need to know, I need to look at the last joint of the last vector, translation vector of the cumulative transformation matrix. So that would be row 0 to 3, index 0, 1, 2, 1, 2, 3. And I really like the format strings in Python now. So you can write things like that. I'm not doing drawing now. So here 0.43, negative 0.52. 0.52 and 0.43 looks about right. So now that will be that. You can change the numbers a little bit. If I have 0 degrees here, it's always good to test your kinematics. Then we end up with negative 0.3, which makes sense, right? Because for this joint here, that's 30 centimeters below. And then if the angle is 0, that means it's along the x-axis, so it's going to go to the right. So what we should have here would be the distance of these three, right? Link 1, link 2, and link 3. And then the foot is kind of like going straight up. And so then there will be 0.55. That's what we get here. So at least we did one sanity check. If I now look at the rotation, let's say I want to move the knee joint by negative 90 degrees, then I end up with negative 0.4 and 0.45. That would be here. Then we're going 25 centimeters to the right and Then we go down by 0.2 and 0.1. So that should be 0.7. I move this to minus 90, then it should keep going down. So right now the length is 0.55. So it goes down to 0.6. Should be this 0.3 plus that doesn't seem right. 0.3. It should be 0.45, 0.55. Oh, here I have the numbers. Oh, let me check. 2, 5, 2, 1. Minus 90. Then I can print it out for each joint. Here, be a little bit better. So here. Yeah, this here is wrong. First we need to rotate, then we need to translate. That's why I said you need to be very careful with right and left translations. So then, why would that have worked? I set all of them to 0. Yeah, this moves along x-axis and at height of 0.33 goes 25, 45, 55. Yeah. And then negative, let's rotate it down the leg. So now we stay at 0 and we go negative 55, negative 75, negative 85. 0, 55, 75, 85, yeah. And now my kinematics should work. See, 0, then bend the knee, then we go up 25, and then 0.3, then 2, and 1. So now I have the correct inverse kinematics, and as you see, the bug was that I wrote these too quickly. First rotation, then translation. And of course, if you want to, you can do it like leave it like this, but you can just put it on one line by adding a dot dot here to do the next matrix multiplication. That will also work. So let's make that a function. Links and thetas. Now, one thing that we can do is, if we are given this situation, I can actually move the joints and then look where the end effector is, right? So for the leg, I can send different control commands, and then I can see where the foot moves to. Because if I have this generation here, let's say these kinematics, and now here I need a one, no, I just need 2, 3, 4, 4 random numbers. And here again, I can only measure the position. Multiplied by 2 times math dot pi here, and the length, okay, in meters from 0 to 1. Okay. More angles, get the links. I need 5, not 4. Oh, okay. So this doesn't look so nice because it has the MP float there. There's a way to format printing the whole thing, but I don't know. I don't remember how to do that. So let's just generate the string. Join. Frags in theaters 2 plus this. Yeah. Oh, no, why? That was correct. Why didn't you complete it? Okay. So I can run some experiments. Ah, not join, not string, but format. And here convert radians into degrees. All right, so now we have the positions and the angles. So now I can run a couple of experiments. So in this case 4, and I send some thetas to the robot, and I measure where the position of the leg is actually. And now what I'm trying to do is figure out what links 2 is, right? That's the secret component. Once I know that, I would be able to derive what the transformation matrices would be. So how can we do that? And this would be called calibrating the kinematics then of the robot. And that's a pretty nice thing, pretty powerful thing that you can do with the real robot. Maybe the documentation is not available, or you made some modifications to the robot, or the material has moved or is a little bit flexible. You can deal with that. Then I actually have to look at the sort of details of my kinematic chain. Which is given in the figure above, but it's kind of looks like this. The body of the robot, one joint, two joints, and then the foot. So here we have O0, J1, J2, J3. Now what I measure is this point here. So I send some random J1s, J2s, J3, and I can figure out what the target location is that I end up with. The unknowns are the lengths of the links. So that will be here, L0, L1, L2, and L3. Right? So how do I take this and convert it into something that I can solve, something that I can optimize? Well, let's have a look at this point here. Right? If I start with 0, 0, then here I get two positions, end effector x and end effector y. And now I need to figure out some equation that allows me to derive length as unknown. So let's just start with L0 and L1 here. Then that would be this position. For now, let's just consider this position here. So that will be L1x, L1y, right? Then I can write that as an equation. So what will be EY? EY would be, first of all, minus L0, right? because we're moving down by L0 along the y-axis. And then so now we're here, we have a coordinate system. So this would be, I have to go down further part like this, right? And that would be L1 multiplied by sine of theta 1. Because here, if it were up, it just now either it's a negative angle or it rotates around. It looks a little bit weird, but if I just draw this and I ask you what's this distance, then you would hopefully all agree that this would be sine theta L1 here. Okay? How about EX? Sorry, L1X? This will be L1Y here, this part. L1Y will be this. So how about L1X? Yeah.
It's L0, that's cosine.
Yeah. So now we have the cosine theta 1 here, right? Okay. Now let's go to, since we're on a roll, let's go to L2, sorry, L2. Well, that's this part from here. How do I get to there? At the next, except almost, but
If it's L2 times cosine of theta 2.
close, but not quite. Yeah?
Theta 1 plus theta 2.
Theta 2, that's right, because it's a cumulative effect. First we rotate here, then we rotate there. So theta 1 plus theta 2, yeah, and then
And 3. Cosine of all the things.
yeah. And here we have L2 sine theta 1 plus theta 2 plus L3 cos theta 1 plus theta 2 plus theta 3, right?
For L3.
Sorry, sine, of course. Right, so which parts do I know and which ones are the unknowns?
The angles are known and the
Yeah, so
unknown.
0 is known, right? This one is an unknown, cos theta 1, all of these are known. So even though they have sine and cosine, but I know what the angles are, so I end up with a number, right? So what do I have here? Or another way of asking is, how many points do I need in order to be able to figure out all the lengths? Length 1, length 2, length 3, length 4. Hmm?
4?
How many tests do I need to run? I need 4 equations. If you have, what? the point is, here, the L0s, the unknowns, those are the important part, right? They're only multiplied by some scalar numbers. Even though the numbers are like the cosine of theta 1 plus theta, doesn't really matter. Whatever it is, it's going to be the cosine of 57, which is some number, 0.23 or whatever. Right? So that means we have scalars multiplied by our unknowns. So this is a system of linear equations. Even though it looks more complicated, it is really not. It is a system of linear equations. In order to solve a system of linear equations with four unknowns, I have four unknowns here, right? L0, L1, L2, L3. I need, no? How many equations? How many non-linear, how many linearly independent equations do I need in order to solve a system of linear equations with four unknowns? No? No. Four. Right? If you have four unknowns, then for a system of linear equations, as long as your equations are not linearly dependent, you can use four equations. Right? But how many tests do I need to run? If I run one test, right, then what's the output of my test? What's the output here? Position, right? Position is the output, and the position is actually there, it's three numbers, right? But one number is always zero, so that doesn't really help us much. But I have two numbers. So every test I run, I get two equations. So if I run two tests, I can figure out exactly what the link lengths are. So let's see if we can implement this in 5 minutes. Now I call it, usually when you do linear algebra, it's always written like AX is equal to B, where A is a matrix and B is a column vector, right? Except I already used A for the transformation matrices. So I'm going to call it B for that matrix, right? So what will the B matrix look like? Well, I need to put these numbers in, right? So that would seem to me the numbers that I need. Feed us to our trials. So I just remember what the angles were that I sent, and I set the output coordinates. So positions. And that will be this, yes. Thank you. And then we have that, and that doesn't. Int object has no attribute. Trial, not trials. Position. Okay. So now I don't want to do any stacking or anything like that. My values that I need to set now is I get 2 rows for my matrix for every trial that I run. So little b1. So that's the row for x. I would need these numbers. So first one would be 0. Zex, yeah, so that would be 0. Then cos, and that would be t0, because that's theta 0, right? Then cos, and now I have to calculate the cumulative sines and cosines here. So that will be, and this is not these brackets, round brackets, and last of cos. T0 plus T1, T0 plus T1 plus T2, so and I think there's only 3. T2, and By would be equal to 1 times L0, and then it will be mass, sines, and there's no Bz. And B dot append Bx, B dot append By, and I shouldn't have called it B because that's B. That's usually the column vector. I forgot about that. Now here I want to append positions 0, because that should be the x position, and then the next one would be the y position. And range length trials. And this would be positions. TI 0, TI 1, T. So here's our 4 trials, the 3 cumulative joints, and then here the positions that we get, 0.37, 0.322, which should be the first 2 here. Right. Now if I have 4, I can actually just solve that. So let's try that, but I'm not sure. np dot layout dot solve db, and I'm not exactly sure what the return is. But yeah. So 1, 3. So I could only do this with 2. So that would be from 0 to 4 with 2 tests, and from 0 to 4, because it must be the square if you solve it this way. And then we get these results here. Now if I print the links to 4, 1, 2, 4. So 5. How come I have 5 here? And how many feeders did I generate? Oh, I generate. Because I generated them randomly, the numbers are wrong. I actually have 5 links, not 4 links, so I'll have to expand. So it's not exactly this robot, it's like there's another additional random link down here. And that's just because I generated random 5 links instead of 4 links. So I generated 5 links and 4 joins, so it's a slightly more complex robot. So that means here we need to add cos T0 plus T1 plus T2 plus T3, and this should be sine T0 plus T1 plus T2 plus T3. T3. Oh, there's more. now I have 5 unknowns, so that and then you can see actually it solves it perfectly, right? Like this is what the output of my calibration. This is what the actual links were. So this is pretty cool. That means you, even if you don't have the exact data for your robot, with a couple of tests you can easily figure out where the home coordinates are or what the exact distances are. So this is quite cool. Now, just lastly, because this is again one of the toolboxes that you should be very familiar with, because it's extremely powerful and can be used many different times. What do we do here? Because I've run 4 experiments, so I actually have 8 equations, right? Not just 5 or 3 trials. So what do I do if I have more equations? More trials. So if I have, like running the trials doesn't take that much time, right? So I can run 5 easily enough, even if I have to do it in practice. I only have 5 unknowns, but if I have 10 trials, then I have 20 equations, right? But I only have 5 unknowns, so then what do I do? So in this case, our system of linear equations is over specified, right? We have more equations than we need. If there's no noise, then it's okay. You can just throw out the other ones and only take the first 5 equations. The tricky part is usually this data here is not pristine, like it's not 100% correct. There's always some noise if you have to measure it, right? So what do we want to do in that case? In that case, what we want to calculate is the least square error approximation. And I'm sure you've done this in high school as well. You want to find the solution that minimizes the errors for all of your calculations, right? So how do we do that? So now my matrix B, if I run 10 tests, then my matrix B is 20 rows, and each one of those will have 1 for each unknown, so I have 5 unknowns, right? So it'll be a 20 by 5 matrix, 20 rows, 5 columns. The unknowns, x, would be 5 by 1, it's a column vector, and b, the lowercase b, which is the positions for trend trials, will be 20 by 1. 20 numbers as a column vector. Now this is a very cool tool that you can use if you want to calculate the least squared error approximation, the LSQ, then because now your system of linear equations is over specified and the exact solution probably won't fit, right? Because the noise will have shifted things around. So there won't be exactly one number that will give you the correct answer for each row. That's why you want to calculate the least squared error approximation. Then what you need to solve, or what you use, is Boyer-Muir pseudo-inverse method. And in order order to calculate the least squared error approximation of your system of linear equation, b times x is equal to b, to get the least squared error approximation, all you have to do is pre-multiply your matrix by its transpose. And we're running a little bit out of time, but what you'll actually see is it'll now, because the transpose, it's going to multiply and basically give you the square of all the differences. And since you pre-multiply on the left, you also have to pre-multiply on the right. So if you, on the B vector here. Now, I have a 20 by 5 matrix, B, right? So B transpose is going to be a 5 by 20 matrix, right? If I multiply a 5 by 20 matrix with a 20 by 5 matrix, then the resulting matrix multiplication, the result of the matrix multiplication is going to be a 5 by 5 matrix, right? And here I have a 20 by 1 vector. I pre-multiply it by a 5 by 20 matrix, BT, so I end up with a 5 by 1 matrix. So at least now the dimensions are correct. As you've seen before, here, this doesn't actually work. Right? I get an error saying that the number of dimensions is not correct. Where does it give me that? Oh, no, not here. This is, if I now use B here, and B, all the points that I have, then I get an error saying that the last two dimensions aren't squared. Right? So now we can run the magic of the Boyer-Moore pseudo-inverse method, and I simply pre-multiply. Actually, there is a numpy.least square algorithm that will do it automatically for you, and it's numerically a little bit more stable, but I can do this. No T. T. And bam, now it works for all of them, right? And okay, fine, that's kind of cool, but you may say, well, it's still a little bit lame. You just get the numbers that we did, but we don't have any noise yet, right? So, okay. Let's make a matrix C, which is the original matrix B plus np dot random length of B. And to make this work, random dot normal or dot normal would be location, scale, and then size. So let's say I take the variance of what are the scale of those? 0.03, 0.01, or 5 centimeters. I assume that the standard deviation of my error is 5 centimeters, and then I add that to my vector B. So all the positions now are shifted by a little bit. So there's some noise added. I can now use C here, which is the noisy vector. And then if I calculate that, then the result is not so good. Okay, 0 0.09, 0 0.4, 41, 39, 20, 25, 40, 77, 83. That may be limited by only having 4. I can now, if I run again and generate more random numbers, let's say 40 trials, then we actually get pretty good data here, even though there's a huge error now. Now 40 trials is maybe a little bit too much to run in practice, but it's not undoable many things, because all you need to do is measure the position of the leg after each trial. Or you can write a computer vision algorithm, put a marker on the position of the leg, and then just look where it is in the camera. So this calibration of the kinematics is can also be quite useful. And the Boyer-Muir pseudo-inverse method is also extremely useful in many different applications. Often if you're trying to estimate things, you're trying to do a least squared error approximation. And here we can implement it in 5 minutes. Oh, actually 23 minutes, but still pretty fast. Okay, good. Any questions? Then the next 2 weeks, the classes are, it's a holiday. Like next Monday is a holiday, and the Monday after that is a holiday as well. So I will post the assignment, so then that gives you at least 3 weeks to work on the assignment. But basically, the first assignment is to build the robot leg and then to control the ball.
Do we use kinematics for it?
No, not really. You would need to, PID control would be useful.
And do you post the exact task for us? Because you weren't sure if we have to balance it only in one direction or more. Or
No, first you do, it's like 3 parts. So first part is in 1 dimension, just along the rail. And the second part is in 2 dimensions. So then that will make the position of the camera, you want to place it on top then rather than on the side. And the first one in the 2-dimensional is to build a little maze and then tilt it this like not as elaborate, but something like this. Right? So you just put that on the top, and then you want to tilt the leg without the leg falling over. Yeah.
And the leg you can do like a foot, knee, and hip.
Pardon?
The leg you can do like a foot joint, knee joint.
Yeah, yeah. Mm-hmm. Well, no. For this one, you need to at least have both planes. So it needs to be able to pitch and roll. For the one in 1 dimension, you could actually get away with just having pitch ankle, pitch knee, and pitch hip. But then you can only rotate in this plane. Right? You can only move in this plane. So there'd be no way to tilt it this way. So you need to have at least one joint to tilt it that way.
Do we have to gather the materials ourselves?
The materials, yes, but we can give you the servo motors. Yeah. But don't destroy the servo motors because we need them back afterwards. And for the materials, cardboard would work. If you wanted to talk to David, maybe you can do some 3D printing, but it's not really necessary. Like I just built it out of the strips. I can post a picture of the humanoid that I built last time. Okay, good.